You know that feeling when you're staring at a probability problem and it's just this wall of text in percentages and your brain just kind of shuts down? Yeah, we've all been there. Well, today we're going to change all that. We're going to take that confusion and turn it into a super clear visual map where you can literally see every possible outcome. We're talking, of course, about probability trees. All right, let's jump right in with a problem I think a lot of us can relate to, a video game boss. So here's the deal. You get 2 shots at this boss. Your first attempt, you've got a pretty good 60% chance of winning. But if you fail, you get a little rattled, and your chance on that second try drops to just 40%. So the big question is, what's your actual probability of beating this boss in the end? Now, you could try to solve this with some complicated formula, but honestly, the best way is to just draw it out. I want you to think of a probability tree less like a scary math diagram and more like one of those choose-your-own-adventure books. It's basically a map. We're going to build a map of this whole story step by step to see where all the paths lead. Okay, so every story has a beginning, right? For us, that's our first attempt at the boss. We start at a single point, and from there, our adventure splits into 2 possible paths. Path 1, success, which has a 0.6 probability. Path 2, fail, with a 0.4 probability. And here's the first key thing to notice. See how 0.6 plus 0.4 equals 1? That's not a coincidence. It's a fundamental rule. At any fork in the road, all the branches have to add up to 1, or 100%. It's a great little sanity check. All right, so what happens on the next step? This is where the tree really starts to show its power. If you went down that success path on your first try, well, game over, you won. That branch just ends. But if you went down the fail path, the story continues. From that point, we draw 2 new branches for our second attempt. We've got a 0.4 chance of success and, well, a 0.6 chance of failing a second time. And just like that, we have our map. We can see every single way this boss fight can end. Now that the map is drawn, we just need 2 super simple golden rules to actually figure out our chances. You can think of these rules as the engine that makes this whole map work. And here it is. This is the secret sauce. Seriously, if you remember nothing else, remember this one little phrase. Multiply along, add across. Got it? Multiply along, add across. This simple slogan is the key to unlocking basically any probability tree problem. So let's break down exactly what that means. It's actually super intuitive. Multiply along is for and situations. You use it when you want to find the chance of a specific sequence of events happening, like you fail and then you succeed. You just multiply the probabilities all the way down that one path. Simple. Then you have add across. This is for or situations. You use this when there's more than one way to get the result you want. You could win on your first try or you could win on your second try. In that case, you figure out the probability for each winning path and then you just add them up. Okay, let's put this into action with our boss fight. We want to know the total chance of winning, right? Well, how many ways can we win? 2. Path 1 is the easy one. Win on the very first try. The probability for that is just 0.6. Done. Path 2 is the more dramatic story. You fail first, and then you win on the second try. Since it's an and situation, we multiply along that path. So that's 0.4 for the fail times 0.4 for the second try success, which gives us 0.16.
And now for the grand finale. We can win with path 1, or we can win with path 2. So what do? We add across. We take the probability of our first winning story, 0.6, and add the probability of our second winning story, 0.16, and that gives us 0.76. So there it is. We have a 76% chance of beating that boss. See how the tree just made that whole process crystal clear? So that video game problem was pretty neat, but the odds were kind of fixed. The second attempt had a 40% chance no matter what. But what happens when the real world gets a little messier? What happens when the outcome of the first thing you do actually changes the odds for the second thing? That's when things get really interesting.
This is what we call dependent events. And the classic go-to example you'll see everywhere is drawing something out of a bag, like marbles or balls or whatever, and not putting it back. Just think about it. The simple act of taking one thing out, it literally changes what's left in the bag for your next draw. The 2 events are now linked.
So let's use a classic example to make this super clear. Imagine a bag with 3 red balls and 2 blue balls. You're going to draw 2 balls, one after the other. And here's the magic phrase, the thing you always need to look for, without putting the first one back. As soon as you see that, a little alarm should go off in your head that says, aha, the probabilities are going to change.
Okay, first draw. This part's straightforward. We've got 5 balls in the bag total, right? And 3 of them are red. So the chance of pulling out a red one is simply 3 out of 5. Easy enough.
Okay, but now this is the crucial moment. Let's imagine we did draw a red ball and we put it on the table next to us. The bag is different now. The whole situation, the entire world of our problem has changed. We're not playing with the same deck anymore, so to speak.
So, what's left in the bag? We started with 5 balls, we took 1 out, so now there are only 4. This is so important, and it's a super common mistake. People remember to change the number of red balls, but they forget that the total number of balls has also changed. The denominator is different now.
So, let's figure out the new probability for our second draw. We started with 3 red balls, but we took 1 out, so there are only 2 red ones left. And we just said there are only 4 balls total left in the bag. So our new chance of drawing another red ball isn't 3 out of 5 anymore, it's 2 out of 4. That's what we call a conditional probability. It's the probability of this event given what happened before.
And to get our final answer, we just go back to our golden rule. We want the probability of drawing a red ball and then another red ball. So we multiply along the path. That's our initial 3/5 times our new probability of 2/4. That gives us 6/20, which simplifies to 0.3, or a 30% chance.
Okay, so games and marbles are great for learning, but where this really shines is in messy, real-world problems. So let's take everything we've learned and apply our mapping tool to something a bit more serious, like medical diagnosis. These kinds of problems can be a real headache without a tree to guide you.
Now, when you first see a problem like this, it's just a bunch of stats. It can be kind of overwhelming. So the very first step, before you even draw a single line, is to just organize the info. Let's break down what we know. First, 5% of people in this population have heart disease. Got it. Then we have 2 conditional stats. If you have heart disease, there's a 73% chance you also have high cholesterol. And if you don't have heart disease, there's a 76% chance you have low cholesterol.
Okay, so with all that data, here's our actual mission. We need to figure out of 100 new patients, how many we'd expect to have high cholesterol. So this is a 2-step process. First, we need to use our tree to find the total probability that any given person has high cholesterol, whether they have heart disease or not. Then we can apply that to our group of 100.
And this is where the tree is just a lifesaver. Let's think, how many ways can a person end up with high cholesterol? 2 ways, right? Path 1, they have heart disease and high cholesterol. So we multiply along that path. 0.05 times 0.73. That gives us 0.0365. Now for path 2, they do not have heart disease, but they still have high cholesterol. Now, the problem gave us a little twist. It told us the chance of having low cholesterol for this group is 0.76. But that's easy. If the chance of low is 0.76, the chance of high must be 1 minus that, which is 0.24. So for this second path, we multiply 0.95, that's the no heart disease part, by 0.24. That gives us 0.228. Since a person can have high cholesterol via path 1 or path 2, we just add those 2 results together.
So after adding those 2 paths, we get a total probability of 0.2645. That means any random person from this group has about a 26.5% chance of having high cholesterol. Now back to our question. How many in a group of 100? We just multiply our probability by 100, and we get 26.45. And since we can't really have 0.45 of a person, we'd say we expect to see about 26 or 27 people with high cholesterol.
All right, you've pretty much got the whole toolkit now. But hey, before you run off and start drawing trees for everything, let's talk about the common mistakes. Let's learn from the pain of others, shall we? Knowing these few common traps will honestly save you a ton of frustration.
Okay, here's a quick checklist of things to watch out for. First, and this is the big one, don't confuse when to multiply and when to add. Just keep chanting that slogan, multiply along, add across. Second, with those without replacement problems, please remember to update the denominator. The total changes, not just the top number. Third, a super quick and easy check. Make sure the branches coming from any single point always add up to 1. If they don't, you've made a mistake somewhere. And finally, a bit more advanced, but for certain given that problems, remember the denominator is the sum of all the possible successful paths, not just one.
So at the end of the day, what is all this about? It's not just about passing a math test. I love this way of putting it. Probability trees are basically decision maps. They take something that feels abstract and uncertain and turn it into a concrete, visual story that you can actually navigate and understand.
And that kind of leaves us with a final, bigger question to chew on. Think about it. How many things in your own life do you treat as certainties? But now that we've learned to map out possibilities, you might start to see that a lot of those certainties, well, they're really just a path with the highest probability on a much, much bigger map. So what in your life might look a little different if you saw it that way?